Okay, good afternoon, people, sir. I think we can start further.
Yeah, okay, ma'am. Yeah, good afternoon, all of you. So welcome back to the third day session of this quantum FDP. So let me begin with what we have left. Yes. So, yes. So we were at this point that we have done drag notation that was called the cat and bra notations. In that cat and bra notation, we have understood that this cat notation and this bra notation. So the cat notation, I was saying that I have also explained to a vector space. So in a vector space, let me recall something. In a vector space, what happens that I was saying you ki every element, I was giving the examples of that is sports ground, examples of kitchen, maybe example of drying area, everything. So in every space, every vector space, what we are calling, we are seeing that at every vector space, there are some elements. There are some sorts of elements in every vector space, right? Group of elements. Okay, so that group of element, we can call it anything else. Element or component or subsystems like that. So, but the thing is that in that vector space, we are having some elements, a non-empty space. In mathematical language, we are calling it as a non-empty spaces, right? So, what I'm saying that we have discussed about this cat vector. So, cat is a object, right? We have described this cat as an object yesterday. And what object? This object must be from any space, any vector space. It doesn't matter the vector space may belongs to kitchen or vector space may belongs to your sports ground or whatever. Okay. So that means at every sports ground or school or kitchen, you are having the some components. And the secondly, I told you that component should follow the multiplication and addition. So multiplication doesn't mean sorry, yeah, there's one point to forget. It may be misunderstood that the addition. This addition is from vector to vector. That is set so vector space set one, vector space set v2, right? But this multiplication is from not the vector to vector. Multiplication is from any number. So we can scale up the vector. So that is scalar. You can say multiply by any scalar. Okay. Yes, any scalar means if V1 is the component, or suppose we are talking about a school, then if in the school, if in a school there is a component, one component which is called book, then it should be, or rather I can say it must be multiplicative. It must have the provision to multiplicate. That means if we are multiplying by 3 or we are multiplying by 5, then whatever, then it can get amplified. That is 15 books like that. So the component should have the provision. Okay. So this is the simple definitions of that. Now, yeah. Why I'm telling you it's not the core mathematics. We have to apply these mathematics, these concepts. So yesterday I was listening some of the feedbacks and I was reading that. So maybe some of all of you among them, some of them may be experiencing this that it's more tending towards the theoretical things. But sorry, about that, yes, it is a theoretical things. Yes, it is not the practical thing to initiation, right? So the quantum computation starts from the theory. It starts from the theory. Okay. So everywhere the human beings are in rush, so they want to directly come onto the casket. So no. So you are not alone. Sorry, sir, you are not alone there in the FDP. There are a lot of people are there in the FDP who want to begin from beginning also. Okay. So maybe whatever the feedback I was reading, maybe that were having experts in this field. So that's why they are feeling it's a theoretical things. Okay. But actually, I have to take all of you, right? So that's why it's compulsion that yes, for the better understanding of all of your FDPs persons, not of 5 or 10 peoples. So we have to take it away from the theory side. So, but yeah, it's a very factual fact. We have to start with the theory. If the theory is not strong, then it would not worth. It will be worthless. Okay. So suppose in a school there is a book. This should be multiplied by. So it will be a 15 books. So it must have the elements must have this much of provision to amplify. Okay. So this scalar multiplication means this one, and this vector addition means the addition of the same type of vectors. So suppose I am talking about the sport person. So in a sports ground, the sport person must be an element. Sorry, a sport person that must be a element of a sports ground, a vector space, right? Then if we are talking that if we are going to add a one person to the another person, then they should have and come out to the same. Suppose this sports person is from cricket and another sport person we can add up from cricket. Okay. So by adding these two sport person, our strength must be amplified and that must return to the cricket also. Okay. Cricket space. Return to the cricket space. Okay. So it's just like that. So well, my intention was not to go in so much depth. Yeah. But there was one point remaining that. Okay. Now, what I was talking about cat vector. So because in any vector space we are having a object to represent element to represent that element is represented by a cat vector. Okay. So that element in a vector space that element in a vector space is not merely a theoretical thing, it's not merely a theoretical thing. We are applying step by step in the quantum computation. Okay. So if there is an element in the vector space, that element is an object. And when it is an object, it must be represented by a cat vector. Okay. So we got object, we are representing as a vector. Okay. Because definition of vector we have seen yesterday, and that is represented by a cat vector. Okay. So now this we have understood that bra vector is also coming there. So the cat vector and bra vector are just transpose. That is, if cat is a column vector, it is a column vector. So bra vector must be a transpose. That is a row vector. So that we can multiply these things and we can have a inner product. We can have a inner product like that. So inner product is always comes in a scalar. I have given an example of thermometer like that yesterday. So now, yeah. So let's move ahead. So in the quantum, so the superposition we have talked about a lot in the our yesterday discussion. The one thing in the superposition I want to tell you so that uh, there is a one concept which is remaining as a normalization, and another concept which is remaining as a Bloch sphere. Now from this Bloch sphere, the theoretical will, I think, will finish. So if somebody was waiting for some things, interesting things, the core quantum computing now begins from today's session. So yeah, so there is a normalization. One concept which is called normalization. And from this concept, a very important concept, which is also one of the main important pillar, is called unitary transformation. It will begin. Our all gates are unitary. Okay, in mathematics, we are representing. My work is to describe it physically. Okay, rather than mathematically. Okay, so that you can get into the soul of the quantum computation. The reason being is that wherever the quantum computation is running, it is in the experimental phase. Somebody was, I was reading something. So somebody was saying that, yeah, it is this technology has always come. No, I will talk about more about this technology in these 3 days. The quantum computation is still in the research phase. So if something has been established, if some technology has been established, then we need not to go in details, so much detail of the theoretical and all these things. Okay. But if this technology is running in the experimental phase, right? So it is not totally evolved. Okay. So in the experimental phase, what was the thing? So it is a thing of product management. So in the product management, what we are doing, there are certain stages of the product, right? Suppose there are 3 stages of product, then the fourth stage, there is a final stage. This is the first stage, second stage, third stage, like that. So the quantum computing is also a product. It's running in these first, second, third, these second stage. Okay. First stage has been closed. Yes, I can say this, but it's running in the second phase. Uh, so the things are happening. If we are making any product, so it's running in the second phase. There are the chances. There are 90% of the chances of research R&D in that phase, second or third phase. So when we are going in R&D and we are finding any error, we have to go back to the first stage. Although these things are not applicable to the classical computation, where the 40 or 50 years have been there for the evolution. So now the classical computation is at its peak. So we have the very running product in the classical computation. So we need not to go in so much detail of its this what is called this basic, because there is no research is needed. Only the application is needed of the classical computation. But when we are studying quantum computation, I am dealing with the 6 or 7 years, especially quantum computation. When we are studying quantum computation, then there is a lot of chances, there is a lot of manipulations is required whenever we are anything, anybody is studying the quantum computation. This research is required. R&D, manipulation is required. In the maybe possible, one of the pillar may be wrong. If somebody will come and they say from their R&D that one of the pillar of superposition, it's not required in the qubit. So we have to change the superposition also. So because it is in the research phase, it is not been established. So here is the theory importance comes. So how you will manipulate when you are not knowing the roots? Okay, so that's why. So if you want a good R&D here, so you have to. It's not. I'm not saying this. Just adopt the roots and from here also. No, no, no. Go on the roots. I'm saying. Okay, and just go on the roots. So just go on the physical significances from where the evolution has beginning in the quantum computation from the hardware as well as software sides. Okay. So yeah, now come to the original point. So that's why the theory was so much important. Okay. But there must be a balance. Yeah, I do agree with this point also. There must be a balance between the theory and practicals. So now this is the third day. So from now we are starting the core quantum and quantum computation, not a quantum mechanics, quantum computation. And all of the 3 days we will have some quiz kit session in the end. So yeah, come to the some concept normalization. Then after the normalization, there is a unitary transformation. In the unitary transformation, always we are saying that there is a U dagger. or whatever, if there is a vector, then U dagger should equal to 1 if U is a gate. Okay. So mathematically, we are representing this as like this. Okay. But there is a one factor which is called one important aspect, which is called normalization. So the normalization, we have to deal with it, normalization. To preserve the normalization, we have to go for the unitary transformation. When we are going for the unitary transformation, it makes us and give us the concept of reversibility, which is very important aspect in the quantum computation. Classical computation is not reversible. Note at this point, reversibility. Okay. So so it's very necessary to understand the normalization. So what is normalization? Only we have to go for the back to the quantum mechanics. In the quantum mechanics, we have studied that there is some possibilities, there is some probabilities. We have to deal with the probabilities, superpositions, and the measurement. Then, when we are dealing with the probabilities, when we are dealing with the probabilities, then then there are certain cases in which we need something important. One minute. So just a minute. Hmm. Yeah. Hmm. Yes. Uh, so we was talking about normalization. Yes. So yes, normalization. So in the normalization, what happens? We are dealing with the probabilities. We are dealing with the psi. So Schrodinger equation was there, and from the Schrodinger equation, just like a term y for the general wave equation, we were having the term psi. Okay. So just like that, y square is giving the amplitude. Here, the psi square is giving the probability of finding the particle, right? Probability of finding the particle. It's giving the probability of finding the particle. Okay. And we have studied that this is the case of wave packet like that. So probability of finding the particle is changing in a wave packet, right? But the whole wave packet is in the universe. The whole wave packet is in the earth, right? So the probability of finding the particle, the total probability, if we want to find out the total probability, we have to integrate. So the total probability of finding the particle must be come out to be unity. The particle, yes, certainly the particle will be somewhere, not within the packet. Wave packet means within the earth or within the universe, right? So the total probability of finding the particle must be equal to the one, right? So this is very important aspect. Okay. So because the total probability must come out to be equal to one, and that's why we need to normalize the cases of this Schrodinger wave equation. That is probability of finding the particle. Why? Because there are a lot of cases we have studied. There is a lot of quantum states occurring from this wave equation. Okay, there are a lot of quantum states are there. When there is a lot of quantum states, suppose there are 50 quantum states like that. There are 50 quantum states. So in all over the 50 quantum states, so this probability 1 has to be distributed. This one has to be distributed in all of the 50 quantum states. So what it means, if we go see on the reverse side, then all of these 50 quantum states must add up to give a unitary, that is this one probability. Okay. So to make it, we are normalizing the things. Okay. So that is called normalization. What normalization? How to make these total equal to 1. Okay. What these total? Probability. Probability of finding the particles in this state, in this state, in this state, and we want to add up like that. We want to add up all these possibilities should come out to be 1. The normalization comes from the word normalize. Normalize means standardize. So we have to standardize the things. So what is the standard here? There has to be some standard. So what is the standard here? The standard here is to make it 1. The probability is 1. The probability 1 is the standard for us. So that means we have to standardize the normalize the things. So that is called normalization. That is, all the possibilities should come out to be 100% or the probability should come out to be 1. So we are talking about in terms of percentage, it should be come out to be 100%. When we are talking to the probability, should be come out to be the 1. Okay. Because the particle may be anywhere, but within the universe, within the earth, like that. Okay. So, and we want to keep this parameter, the probability should be 1. We want to keep this parameter constant if the system are changing. The quantum system, if the quantum systems are changed, so that means we are talking about what we are talking. Change means, change means we are talking about cat vector. Cat vector is a column vector, right? State vector, we can say state vector. It represents the state of an object. Okay. And bra vector, it's a measuring device. Bra vector is a measuring device. So when this cat vector is operated on the measuring device, okay, so then we are getting a scalar quantity. Right? So that's, so when something cat is operated on this measuring device, so that means that means we are talking about transformation. Okay. So physically we are saying that thermometer is there, it has to be operated on the hot object is there, it has to be operated on the measuring devices like that. But when we are coming on to the quantum computation, we can say that there is a quantum state, there must be a quantum state psi 1, psi. It has to be operated on some operator. Operator is called the measuring device at here. That is a bra operator. It has to be, suppose I'm talking about operator U, it has to be operated on U operator. After operating in the U, it must transform to the psi dash, suppose. Right? So it is transforming to the new system. It is transforming to the new system. This is a new system. Right? So when it is transforming to the new system, and we are saying that we have to conserve this normalization. Please go beyond this concept. We are saying that we have standardized our parameter. What the parameter? Probability should remain 1. So it should remain 1 at this side also. It should remain 1 at this side also. So this is a play. Okay. So everywhere in the next quantum algorithm, in the quantum gates, everywhere there is a play. Because quantum gates are nothing. It is just like a operator. So just like U. So U is a universal quantum gate. Okay, suppose. Okay. U is the universal quantum gate. And if this quantum gate is applying on some quantum state, that quantum state may be 1, 0, maybe 0, 1, like that. This study we are talking about. It may be 1, 0 column vector. It may be 0, 1 column vector. So if this applies mathematically on the quantum gate, unitary quantum gate, then the probability it is changing to the new system. Let us clear these things. So it is changing in the new system. When it is changing in the new system, that is psi1 it is a new system, then this psi1 is a new system, then in all the both the systems, this condition must preserve. So to preserve this condition, we are getting, there is some derivation for that. We are not going into so much detail, but mathematically, but physically, there is a system. So when we have to preserve this normalization, that is probability 1, then we are getting the derivation starting from that condition. We are getting this derivation U dagger come out to be 1. So that is the concept of this concept is called unitary. When we have arrived at this concept, it means this operator we are calling it a unitary operator. Why the unitary operator? See there, if you are talking U, so this is 1 over U dagger, like that. So it is just opposite. We can say that this operator in the new system, this operator is just opposite. Okay. So that means if it is just opposite, so that means both are giving us, and both opposite in such a way that both are giving us a unitary value. That's why it is called the unitary transformation. In other words, we can also say that unitary transformation are reversible transformation. Reversible transformation. Okay. Unitary transformation or reversible transformation. And this is very important aspect of the quantum computation. The unitary is reversibility. Okay. Why is it reversibility? Because it is getting 1. So we can also do like this. U dagger is equal to 1 upon U. There is no difference between these two. We will change it. There is no difference between these two. Either this or this. See, that's why it is called the unitary transformation, and that's why it is reversible. There is no difference from here to here, or no difference from here to here. Okay, either we can go in both the way. That's why the unitary transformation is also called the reversible transformation. And why the unitary? You can start from this path. There is a reversibility followed in the quantum computation. Okay, let's clear these things. The unitary, sorry, yeah, the reversibility in the quantum computation, that is coming from unitary transformation. Okay, unitary transformation. And this unitary transformation is coming from because we want to conserve the, you can say conserve, it's a more common term. We want to conserve the probability, which is 1. Okay. And why we want to conserve the probability 1? Because it is the rule of nature. Rule of nature. See, nature doesn't allow to leak the possibility of probability. If we are talking about there is a A, B, and C, 3 components are there. And suppose we are talking the A component contribution is 30%. And suppose B component contribution is 40% or 45%. Okay. And we are saying now there is a total, and we are saying nothing about C. So there is only total of 75%. So if we are omitting C, if we are taking only A and B, then it is not possible, because nature itself says, the percentage rule itself says there must be 100%. So where the 25% has gone? So we must assign this 25% to anything, for anybody. So it is just like that. Nature, this is the nature. This is the nature. 100%. To make it 100% is the nature. So we cannot allow somebody to leak out the possibility of probability. If the probability is one in one system, it is going from one system to another system. If the probability is one in this system, probability has to be one in this system. Okay, to conserve the probability, this is the rule of the nature. So you can say there is a rule of the nature to conserve the possibility of probability one, which gives us the unitary, which gives us the reversibility. Okay. So overall, these are the total concept of reversibility and unitary. Now we are moving out to the Bloch sphere. Now it's starting off, although we have started the cat and bra notations, but now it is the legally you can say, officially you can say, starting off quantum computation, hardcore quantum computation from Bloch sphere. Okay. So now, yeah, one thing is also remaining that when we have studied the superposition, okay, we will be continuing studying the superposition because we want to study the quantum algorithm. Also, the quantum algorithm based on the superposition. Without the superposition, we can't do in the algorithm. Okay. So when there is a superposition, so superposition doesn't means that, see, if I was talking about, suppose I was talking about this wave yesterday, this wave, and we will see another color. I was talking about another wave, and this is one condition. Another condition is that I was talking about this condition. Another is this condition. There are two conditions we have talked about. Okay. So this is also the superposition. Just see that it is also called a superposition in a same phase. And this is also called a superposition in opposite phase. Okay. And we have seen also that this is the maximum, this is the minimum. Between the maximum, this is the maximum, this is the minimum. I'm not coming again and again, but yeah, concepts are compelling me to come again and again on that point. Sorry. So from maxima to minima, there must be a different stages. Okay. I just talked about yesterday 5.7, 7.6, 1.3 like that. And we are going to add it. Okay. So superposition, every state is a superposition state. Every state is a superposition state, but every state is a different. See, every state is a different, right? Every state is a superposition state. This is different. This is different. And in between of that, this must be different. This must be different. This must be, and this must be a different things. Different stages. Different states. Okay. What makes a different? Anybody can chat it. What makes the difference? What is the difference? The difference is lies in the phase. Okay. The difference, what is the difference? Difference lies in the phase. Okay. This is in the same phase. This is in the opposite phase. And when we are talking in the middle, it will be in a some in middle of that phase, some in middle of that phase, not same, not opposite, like that. Okay. Yesterday we talked a lot about this, right? So these conditions, all this is superposition, superposition of the two, one and two. We can call it superposition of one and two. This all, suppose if we have 70 states, if there are 70 states, so all these 70 states are coming from the superposition of one and two, one and two waves. Okay, we can call it wave one and wave like that. Okay. So what makes it different? These 70 states, that which is called a phase. The phase makes a different in different 70 states. Okay. So to represent this phase, or we can say, if there is any convenient way to represent all these 70 things, so that convenient way to represent all that 70 states with the different phases is on the sphere. This is a convenient way to represent. Okay. On that sphere, on the surface of the sphere, on the surface of the sphere, like that. here, 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 here. Okay. So suppose if I will take this is a center. Okay, let me make a perfect sphere. Hmm. So let's make it. Yes. I think, yeah. So if there is a sphere and in this sphere it is a center. So if we can, oh, one thing, one thing remaining. Suppose 70 states. Suppose now we are coming to the quantum computation. In the quantum computation, we are saying our cat vectors and bra vectors. All these vectors are representation of basic states are 1 and 0, right? Basic states are 1 and 0. Okay. So there may be 1, there may be 0, there may be a mix of 1 and 0s. So we want to represent directly. Okay. So this representation directly coming in this. Okay. So we can represent 1 and 0. So 1 means cat 1, 0 means cat 0. Okay. 1 means cat 1, 0 means cat 0. Now cat 1, I already told us that this is something 0, 1. This is something 1, 0 column matrix. Okay. So there are cat 1 and cat 0. What they are, always remember, at least when I'm teaching there here. So if it will come in 50 times, then it will be embedded in your mind. Okay. So when we are talking about cat 1, cat 0, okay, then we are talking about object. Okay, object in any vector space. We are talking about object in any vector space. Okay. So when we are talking about object of any vector space, which is represented by a column matrix like that, which is represented by a column matrix like that. And why we are taking a 0 and 1? Because 0 and 1 are the basic states. Either particle can be present or not. Either yes or no. So these are the basic states. So yesterday I talked about like that. The basic state ijk. So we are representing basic state 2i plus 3j like that. 2i plus 3j. So we are representing in the form of basic state I and j. These are the unit vectors. Okay. So just like that, we are representing here the basic states are 0 and 1, yes or no, like that. So we are representing column matrix. So if we want to represent 2i plus 3j as a column matrix, we can represent like this, 2 and 3. This is. So just like that, we are representing 0 and 1, 1 and 0. If somebody is thinking about why the 0 and 1 and 0 like that. So that's why. Same analogy. So let me clear some of the things. It looks like a very meshy. That's why I claim this. Yes. So yeah. So always remember this cat vector is an object of any vector space. Okay. Then vector space means this quantum computation. Okay. So basic states are 0 and 1. 0 and 1 just analogous to the I and J on the conventional coordinate geometry. Okay. I and J are the unit vectors. 0 and 1 are the unit vector right here. So we are representing this as this. So if we want to represent 1 and 0, so we can donate extreme cases. Okay, we can donate extreme cases here. This is the north, this is the south pole. Okay. So in the north pole, we can represent anything, but there is a convention. So okay. So in the north pole, we can represent cat 1, cat 1. Here we can represent cat 0. Okay. So if North Pole is cat 1, South Pole is cat 0, now all of you can understand if we are somewhere at the surface of the uh, if we are at somewhere at the surface of the sphere, then it means it is the combination of 0 and 1. This is the different combination of 0 and 1. This is the different combination of 0 and 1. Okay. So as we move towards this side, there is a different combination of 0 and 1. But suppose we are talking about this point. Suppose we are interested in this point. So this point in whole of this circle like that. This point 0 and 1 combination, there is a combination of 0, 1. So combination of 0, 1 is same for all the points at this circle. Yes? Yes. I think so. So in this circle, circumference of the circle, this is called a, suppose this is in middle, then it is called a great circle. Then all the points will be at the same combination of superposition of 0 and 1. Because from here it's the same distance, from here it is the same distance. Okay. So all these points are on the same combination of 0 and 1, superposition of 0 and 1. But still, this is a different, this will be different, this will be different, this will be different, this will be different. There are hundred of points, there are infinite points, we can say, and each point will be different. Different in what? Different in these perspective. Okay? Different in this perspective, maximum and minimum, like that. Because, and we have talked about the 70 different states. This is just for example, it's not merely means the 70 states are there really. So for example, 70 different states are different in this perspective. So to represent these perspectives or different perspectives, we have a very good representation. This representation is called Bloch sphere. This sphere is called the Bloch sphere. So at one side, we have donated work at 1. At other side, we have donated a 0. So all around these things, all around the surface of these points are representing different combinations of 0 and 1. But if we are talking about at a one circle, circumference of the one height, then there will be a same superposition of 0 and 1, but in different states. Yes. And what are the difference? Difference is in phase. So if let's say here, if on this point, if this is in this phase, then on this point it will be an opposite phase, definitely. Okay. At this point, it will be a different phase, like that. Like that. Okay. So there are different phases along this circumference of the great circle. Right? Although the superposition, it is all these points are called the same superposition of 1 and 0, but in different phases. But in different phases. Right? So just understand this Bloch sphere. Okay. So yes. When now we have talked about unitary transformation, we are going from system 1 to system 2, system 1 to system 2. So when we are going from system 1 to system 2, the very first basic thing is that there is a one criteria which remains preserved, probability should be 1. When probability, to preserve this probability, we need a unitary transformation. Unitary transformation. Okay. And so how to go from system 1 to system 2? By operator. By operator. Okay. By operator. So, and what is this operator? This we are going to design. This we are going to study now. What is this operator? So I hope you are following the pattern and the pace and the consequence, not consequence, sorry, sequence. So what the sequence we are aligning there? So so now we are introducing, so this we have introduced the Bloch sphere to represent the different phase structures. Now we can say, so you can say also the Bloch sphere is used to represent the different phase. Okay, the different phase. And why sphere? Sphere of same radius. Why the sphere of same radius? Because when the sphere is of same radius, then the probability will remain conserved. It will not go beyond that. Okay, it will not go beyond that. No, it will not go beyond that. The probability will remain conserved and one. That is called one. Okay. And we why from where this idea has come? Idea is coming from the hardcore math. In the hardcore math, if somebody is or I think all of us are from science background, or if somebody is from not science background, I think she or he may also be getting this. So this idea is coming from exponential function, that is e की power I theta. Okay, we know that e की power I theta. Okay, r e की power I theta like that. So the mod of this e की power I theta is always one. Sin square theta plus cos square theta is one. So this ideas came. So there is no better way to represent all these quantum states, 70 states, 100 states, 200 states like that from the Bloch sphere. Okay. So the Bloch sphere is used to represent the different combination of 0 and 1. And if there are same combination of 0 and 1, then in the same combination, there is a different phases, right? So it's just like a latitude and longitude when going from the Earth. Okay. So you can take the same analogy here. That this is altitude and longitude things. Okay. So when we are going around latitude and longitude, the phase may change, the superposition of 0 and 1 may change. If the superposition of 0 and 1 is not changing, it means we are not changing our one of the parameters. Then the phase will change. Okay. Then the phase will change. If we are going on this side, then some other parameter, latitude or longitude will change like that. So it is overall, there is no better way to represent this as a Bloch sphere. Okay. So Bloch sphere will give you the number of states either from the perspective of different 0 and 1. Let me clear for these things. Either from the different perspective of different 1 and 0. If this is the case, then it can also be represented from the Bloch sphere. And it also gives us the points to represent where there is the same 1 and 0, same combination. Same combination of 1 and 0, but different phase. Yeah, writing is somewhat typical because my tablet is not working. Phase. Okay. So both ways we can represent in a Bloch sphere. Okay. So now I think you are completely understand the what is Bloch sphere. It is used to represent the different states of different combinations of 1 and 0, as well as in the same combination of 1 and 0, if it is in the same combination of 1 and 0, it is used to represent uh, different phases along among the same combination. Okay. So combinedly, everything we can represent in a Bloch sphere. Now, the thing is that when we are going to apply a transformation from system 1 to system 2, when there is a transformation from system 1 to system 2, we have to apply operator. These operators are called gates. These operators are called gates, and we know from going from system 1 to system 2, these operators should apply in such a way. So these gates should apply in such a way, it should be a unitary transformation. It should be a unitary transformation. Why should be unitary transformation? To conserve this parameter probability 1, okay, in both the systems, because nature allows it. Nature doesn't allow that probability will leak out. Okay. So probability should remain conserved. It is, you will not question if somebody is saying that there is 100%, and somebody is saying only two contributors are there, 70 and 45 and 30, right? So it is automatically understood that 25% contribution from somewhere. Okay. So probability must not increase, probability must not decrease, should remain the same possibility. One of the example I can say that uh, because we are talking in a wave, so wave of yesterday we were talking about water waves. So the water waves, if the water wave is forming in the pond, suppose there is a pond, okay? If the water waves are forming among the pond, if the water waves are forming in these ponds, then what is differing? That is probability of finding the water at somewhere. What these waves are taking away or taking towards water, right? Water, okay? So the possibility of finding the water may be different at different places, but the total possibility of finding the water, it will not go beyond the pond. Okay, so the total water will remain conserved, right? So just take the analogy of this thing. If we are taking for the matter wave, so in the matter wave, the total probability of finding the particle is conserved. So there is a distribution of water at here. Just like that, there is a distribution of probability at different points on the wave and in the pond. But it doesn't mean that the total quantity of water is going to change. So the total quantity of matter, total quantity of probability is remains the same. That is a nature. From that nature, unity transformation coming. From that nature, gates are coming. So the gates should always be unity transformation. So that's sufficient for all these concepts. Now we are moving towards the quantum gates. Okay. So yes, superposition. We have unitary operators. We have understood. Okay. So David, there was a David. So we are going to study this algorithm, but before the algorithm, they has already said something. He has conceptualized the requirement of the quantum Turing machine. Okay, the Turing machine, that was the hypothetical one. Okay, so there was a classical Turing machine. Now there is a quantum Turing machine, which is synthesized or conceptualized by David. Okay, so this point, gate must be unitary and reversible. I have explained to you, and the matrix-based transformation on qubit. So when there is a matrix, there will be operator. Okay. So now coming to the single qubit gate. So there are uh, mm, two types of gates are there. So first I will summarize of qubit. Okay. From single qubit gate, we need to summarize three or four things. First thing is that what is qubit? Qubit is a superposition of 0 and 1. These 0 and 1s we can represent by a cat vector. First thing. Second thing, these 0 and 1 we are representing by a cat vector, that is cat 0 and cat 1. Okay. So cat 0, that is representation of cat 0 is this one. Representation of cat 1 is this one. And third thing, there is a superposition. The superposition we can represent like that. For representing the superposition, we are taking the coefficient alpha and beta to be in 0 and 1 state, corresponding to 0 and 1 state. So the superposition state, there is the alpha possibility or probability of being in 0 state and beta possibility of being in 1 state, like that. So this is the superposition state. So for the qubit, for a one qubit, we can have these three standardized things. For one qubit, we can have these three standardized things. What are these three standardized things? One is cat 0, one is cat 1, another is superposition, which is called alpha cat 0 plus beta cat 1. Okay. This is 0, cat 1, and superposition of alpha cat 0 plus beta cat 1. And this superposition state, which we had talked about in the first day, it can be divided in finite states. It can be divided in finite states. Okay. But combinedly, we are saying that it's a superposition state. Either in the same phase or in different phases, we can represent like this. Okay. So whenever there is a one qubit, so there is represented by this. And this superposition state, taking the analogy from the Schrodinger, we are representing like this psi. So psi state must be alpha 0 plus beta 1. There will be different values of alpha and beta. Yesterday, before yesterday, we have talked about that. 70%, 30%, 69%, 31%, like that. So alpha beta may take the values from 1 to 100. Okay. If this is the case, the value of alpha will be 100. If this is the case, value of beta will be 100 and the value of alpha 0. Okay. So this is the one qubit. This is the representation of one qubit. Okay. In the Bloch sphere, we are representing this one qubit like that. There is a 1, there is a 0. Okay. And we are representing along this point. Okay. Till now, we have studied these things. Now we are moving towards operators. So operators, from we want to transform from system 1 to system 2. Okay. So why we want to transform from system 1 to system 2? This is coming from also from Schrodinger equation. Okay. So in the Schrodinger equation, when we are coming reading the Schrodinger equation, I'm not going to depth, only I'm telling when we are reading Schrodinger equation, then in the Schrodinger equation, there is a time evaluation and space evaluation. So space evaluation and time evaluation, because the every state is not stable. Okay. So the quantum state is not stable. It follows from the uncertainty. Uncertainty, the probability is changing from time to time. So that means the system is not stable. Okay. So there was one question from one student. So whenever I was talking like this, we have to go from system 1 to system 2. So the person is asking that, but sir, why we want to go from system 1 to system 2? What is the need for this? This is not the need for need. This is not the need of any component. This is the nature. Nature always evolve, always changes. Okay. So because the uncertainty follows from the nature, nature always changes. The system always changes from 1 to 2 to 3 to 4 like that. We have to choose such a rules now in the quantum computation because we want knowingly. Yes, Supriya raised her hand. Yes, please have it checked. Yes. 1 minute. Okay. Yes. Yes. So, so there is a demand from our side. Finman said, na, only the Finman said that we have to move from classical to quantum system because the nature deals in quantum. And when we are moving in the quantum system, so it is our compulsion. Okay, this is our compulsion. We want to deal with the quantum system. The quantum nature of the quantum system is like that. They always keep revolving. So that's why we are going from system 1 to system 2. Okay. So, this is the nature. This is the nature. Okay. Most of the things comes from the nature in the quantum. Okay. So I'm saying it's just like a planned city. Now we want to control these things. Okay. From system 1 to system 2. We cannot let go this system 1 to system 2 anonymously. Okay. At randomly. No. We have to choose. The choice is in our hand. What we have to choose? We have to choose such an operator which must be unitary. We have to choose such a operator which conserve the probability. Okay, so this is in our hand. So to keep reminding these things to choose in such a way, we are moving towards the single qubit gate. Okay, so now just follow the pace of the my designed course, that now we are going to move on the this unitary operators. And these unitary operators, we have to choose. This is our choice. Okay. So we have to choose in such a way the probability remains conserved. It must be unitary. Unitary giving us one more advantage, that is reversibility. Okay. That is reversibility. All that's are coming in coming in the say now. So if we are taking purchasing one thing from, so another thing is free. So we are conserving our probability here, but conserving the probability, there is one more free item is coming, that is reversibility. And this is very much important aspect of the quantum computation. Okay. So now what is our work? We have to choose such a operator. Now to choose such a operator, I'm just yeah. Now to choose such an operator, there is also we also have to look up from the physics point of view. Okay, so sorry, whoever is saying it's a theoretical things. We have to look up from the physics point of view. Okay, if you are following my pace, then you will not say it's a theoretical thing. Uh, so if you are forgetting my pace, then it may be. Okay. Yeah, I'm saying, so unitary operator, how to choose the unitary operator in such a way it will follow our requirements. Going from system 1 or 2, nobody will disturb, the probability will not leak out. So we have to look up for the quantum mechanics also, and that is coming from Pauli. This quantum mechanics we have to follow from Pauli. Pauli in 1930, among 1930 or 27 to 30, I think, 27 to 30, Pauli has formulated some matrix formulation along with Heisenberg, and they has pre-deduced some matrix form. That matrix form is like this. Coincidentally, it is found like that. It is found like that that the it's found like that it's conserving the our requirement. All these three, the polys X, Y, and Z, all these three are and they are very eligible on our parameters. Okay. So what are this X, Y, Z, and Pauli also, along when they were driving all these threes, they have also derived that there are two properties in the Pauli, and these two properties are matching with our requirement. Okay. So these two properties are like that. X is, if there is X, Y, Z, Pauli X, Y, Z, these are generally called in quantum mechanics. So X combined with X dagger. Okay. Oh, sorry. First property is not combined. So second property. The first property is, let me delete this thing. So X is equal to X dagger. Okay. I think everybody will know the dagger. Dagger is the combination of two. Dagger is the operator and the combination of two operators in the matrix, right? So in the class 12, everybody knows this. Okay. So combination means first you just take uh, complex conjugate, then you just take the transpose. Okay. So yeah, so X is equal to X dagger. This is the property of this matrix. Okay. Let me remove everything. Amnesia. Yeah. This is X, this is Y, this is Z. Now our requirement is unitary of unitary. And unitary, when we are following this unitary, the mathematical form of this unitary will come out to be U dagger must be 1. So in 1927, 13, Pauli also has reduced these things. So this is called Pauli X matrix, Pauli Y matrix, Pauli Z matrix. Actually, he was working on the spin of the electron. He was working on the electron spin. Okay. So he was working on the electron spin. So when he is driving the spin is equal to 1 by 2 and minus 1 by 2 like that. So in the way of driving spin 1 by 2 and minus 1 by 2, they have come across these matrices. So that was the mathematical derivation, and that mathematics come from these inputs, X, Y, Z matrices. Okay. So coincidentally, these matrices are, yeah, we were discussing about property. So first property is that X is equal to the X dagger. And the second property is that either X or Y, same for the Y, same for the Z. And second property is X dagger is equal to 1. X dagger is equal to 1. Same for Y, same for Z. Okay. So we have found from the earlier discovery, we have found our requirement now. So the requirements are X gate, Y gate, and Z gate. And these are the operating matrices for this YZ, X, Y, and Z gates. Okay. So I need not to be described these things. Okay. Matrices. Okay. 0, 1, 1, 0, 0, I minus I, like that. Okay. So this is Pauli X, Y, and Z gates. Okay. Now, so in a single qubit gate, when we want to operate, we can operate like this in this way, that mathematically, if we will show this, there is a cat, suppose firstly for cat 1, if there is a cat 1, which is operated on the polymetrics, that is X, operated on the polymetrics, that is X. Okay, the X is 0, 1, 1, 0. When this 1 will operate on that, so there will be a multiplication, and by multiplication, you can know that it will come out to be cat 0. Why? Because this cat 1, we know this cat 1 matrix is 0, 1. Okay. And there is a simple matrix multiplication row by column. Just go and you will came on this conclusion. Okay. So generally directly I have written these conclusions by matrix multiplication, that if we are taking input as a 0, if we are taking input as a 1, we have the three possibilities, right? We have the three possibilities, either 0, either 1, or mixed state. Mixed, which is called superposition state. Okay. So when we are inputting 0, so this matrix allows us, this matrix calculation is that when we are inputting 0, it's converting into the 1. When we are inputting 1, it's converting into the 0. Okay. X gate. And the same thing we will do on the Y matrix. It will convert into 0, convert into this one. This convert into this one. Okay. Same will go for the Z. This will convert into this one. This will convert into this one. Okay. And to remember this, see, this I have not mentioned. So when these two are known, this can be known, because this is a superposition of 0 and 1, right? See, again, this is the superposition of 0 and 1 here, right? So when applying 0, it is getting 1. Applying 1, it is getting 0. Just reverse. 0, getting 1, 1, getting 0. That's why we are not worried about this mixed state. If you know this, you can know this, right? Like that. So this is operation of a single qubit gate. So I have a general slide for that. 1 minute. Let me go through. Hmm. Yes. So there is a slide. I hope the screen shared. This whiteboard is coming to all of you. Hmm. So 1 minute, 1 minute, 1 minute. Hmm. Yes. So this is the X gate to travel. This is the Y gate to travel. This is the Z gate to travel. And see the difference. Okay. So in the X gate to travel, it's just like a NOT gate, whatever we are studying in the things, in the classical things. Okay. It is just like NOT gate, NOT gate. Okay. Y gate is nothing. Y gate is following something, another logic. So see here, the logic is it's only, see why I we are seeing here, because there is a I in the matrix. Okay. The I was in matrix. I will also paste that matrix at here. 1 minute. Mm, yes. See, see the I is coming here. The I is coming at here also because of complex quantities. Complex quantities. Because Schrodinger equation deals with the psi, and the psi is coming to be a complex quantity. Okay. So when psi is coming to the complex quantity, and it is a hardcore reality. So Pauli is following the Schrodinger. When Pauli is following the Schrodinger, so he also gave this concept of I. This is coming in the derivation. So what it means, I means change of phase. Okay. So from change of phase from 10201 from real to imaginary. So I represent the imaginary. So from real to imaginary, from real to imaginary. Okay. Or from imaginary to real. There is a system changing phenomena. Okay. So, and also there is a -1 is also coming. So -1 means we can change if there is a Bloch sphere. So -1 means we can directly change from here to coming at here. This is okay. This is negative. Okay. And -1 means if we are at here, we have to come at here. Okay. So this is the representation. So just like this, see the X gate is just like a NOT gate. It's just inverting everything. Y gate, it is inverting also. It is inverting also. Follow that. It is inverting also, but with the imaginary systems. It is inverting also, but with the imaginary systems. 1 to 0, 0 to 1. One adding imaginary system. Okay. Z gate. Z gate is also called phase. It impart the phase. But when it impart the phase, it reverses the phase. But when? When there is a 1. When the system is in one phase, cat 1, then it will reverse the phase. That is 1 to -1. Okay. So Z gate is reversing. It doesn't do anything to 0, but it reverses the phase when it is in 1. Okay. So these are logics coming from the directly from the drug, directly from the polys. So the poly X, Y, and Z gates, we have made it at here. Okay. That is taken from the polys X, Y, and Z matrices. Okay. So the two properties of the matrices are like that. X is equal to the X dagger, makes it unitary, and it means X dagger is 1. Okay. It means X dagger is 1. So these two properties following by the X, Y, Z gates. Okay. So now coming to the, this is the single qubit gates. All these gates are single qubit gates. Okay. Now coming to the multi-qubit gates. For the multi-qubit, I have to share 1 minute. I have to share the presentation. So these are single qubit gate, and there is one more Hadamard gate. So Hadamard gate is used. Actually, I should introduce like this. So Hadamard gate, its matrix. Hadamard gate is just like a operator. This operator we have to choose in such a way. There is our choice. The choice is there. There is in such a way it has to be unitary. So the Hadamard gate matrix is also coming from not from physics. This matrix is coming from earlier work of any mathematician. Okay. So that matrix is also, I'm just giving you 1 minute. Um, Matrix, where is this? Yeah, quantum gates. So you can follow the Wikipedia page. From that, I'm copy and pasting here. So see, Hadamard gate. So there is a matrix for the Hadamard gate. This matrix is already came from mathematician who is already discovered. So we have the choice. Actually, we had the choice and we were searching for that choice. So all these matrices are not coming at randomly. So all these matrices are our choice. We were searching which matrix will give us a unitary transformation or reversibility transformation. So these matrices are coming frequently successful on that parameter, right? So the Hadamard gate matrix is like this, and you can do now the same multiplication. Okay, same multiplication. Now what it will do? It will just superimpose the things. Superimpose the things means when you will apply a 0, it will superimpose cat 0 plus cat 1. Both superimposition will be there by root 2. It will give you this, okay? And this result is followed by the mathematical operation matrix multiplication in the same manner as we have done in X, Y, and Z cases, okay? For the 1, it will give you 0 minus 1 by root 2, okay? So the Hadamard gate is used to, always remember, the Hadamard gate is used to superimpose the two states. Okay, superimpose the two states. This state is called positive state. This state is called negative state. Okay, positive cat, negative cat, positive cat, negative state. So the Hadamard gate, whenever in the quantum circuit, if it will be used, whenever we will use the Hadamard gate, it means we are superposing the inputs. So in the quantum circuits, now we are going to study the quantum circuits. After these gates, then in the quantum circuits, if we are inputting one thing, that this one, we are again inputting another thing, this one, and we want to make superposition of these two things, we have to use the Hadamard gate. You can follow the Wikipedia page. Okay, the quantum gates, Wikipedia page of quantum gates, right? So these are the symbols: X gate, Y gate, Z gate are the symbols. Hadamard gate. Now, in the same manner, we are having the matrix. Matrix. We were in the search of the matrix while formulating these things. Then the matrix we have found like that, which is rotating the phase. That's why it is called the phase gate. Now, this matrix is rotating the phase by pi by 8. Okay, so that's why it is called this matrix. Okay, so now coming to the now till this point, now till this point, till this point, there are single qubit gate SQB. Okay, so all these gates are called single qubit. That is, we are inputting cat 0, or we are inputting cat 1, or we are inputting superposition of that cat 0 and cat 1. Superposition of this. Okay, that is alpha plus beta, like that. But we are inputting superposition. Oh, sorry, single qubit. Single qubit means either yes or no. Either yes or no, or the combination of yes or no only. But now coming to the multi-qubit gates. So what will happen for the multi-qubit gates? When there will be a multi-states. So for the multi-qubit gates, we require first the input matrix. We require the input matrix. Okay. The second thing, we required the number of states. Okay. Second thing, we require the number of states. So all this for the input matrix, we have to look up for the 1 minute. Oh, we have lost this. Oh. Yes. For the input matrix, input factor matrix means, because we are having cat 0. Cat 0 is input matrix is this one. We have described. Cat 1 input matrix is 0, 1. When we are having an input matrix, and we are having a this transformation matrix. This matrix is called transformation matrix. Okay, you can edit transformation matrix. Okay, you can cut, copy, paste from the Wikipedia and then edit transformation matrix. So these matrices are called the transformation matrix. So for the multiplication, for the operations, we need the two things. Okay, we need the two things. The first is called the input matrix. Okay, this is the first thing. Then second, we need a transformation matrix which will transform. Okay, then it will be applied and will give us the final result. Output will give us the output. Okay, so when we are having a single qubit 0 and 1, we are having these matrices. Okay, but when we are going on to the multiple qubit gates, so the input matrix we have to find out. The input matrix we have to find out. This input matrix we can find out from the tensor product. Okay. This input matrix we can find out from the tensor product. Okay. So the tensor product is nothing, only the called outer product. The tensor product is nothing, it is called outer product. Okay. First, we have to find out this input matrix. Then this transformation matrix we knows. From where it is coming, we'll tell you. Okay, the transformation matrix. Input matrix we will find out from the tensor product. Transformation matrix we are having. We can have the mathematics. We can have the multiplication of the matrices. Then we can go for the output for the multi. Okay, and yeah, things. Second is to count is number of states. So when we are having a single qubit, this is a single qubit. The number of states 0 and 1. Right? Like in classical. In classical, if we talk about classical, Then in classical, when there is a bit, there is a 1 bit, it is having a state 0 and 1. But when it is 2 bit, it is having a state now 0, 0, 0, 1, 1, 0, and 1, 1. Right? These 4 states we will have. For the 3 bits, and just like that, 8 states. 8. Okay? And for the n bits, we are having formula that is 2 to the power n states. N states. Right? Right? So just like that, here the number of states we are having, suppose on the 2 qubit, if there is a 2 qubit, the number 2 qubits, the number of states will be same, that is 4. That is 2 to the power 2. That is 4. Right? For the 3 qubits, 3 qubits, 2 to the power 3. That is 8 states. That is 8 states we will have. Right? So, okay. So we have find out now how to find out the input matrix by the tensor product, how to find out the number of states with this formula. Okay. Now the main thing is that here there is only 2 states. That's why we are representing alpha. We are taking alpha and beta, and we are representing in the superposition form by adding these two, alpha 0 plus beta 1. Okay. This was the single qubit. But when we are coming to the multi-qubit or double qubit or 3 qubits, then what we have to do? Now just see. Mhm. So when we are coming to the Mhm. So when there is a multi-qubit, then the number of states will be like that. Instead of cat 0, it will be cat 0, 0. It will be cat 0, 1. It will be 1, 1. No, sorry, 1, 0. It will be cat 1, 1. Okay. There are 4 states for the 2 qubit. So we have to take more coefficient alpha, beta, gamma like that. So we are taking, suppose we are taking A, B, C, and D coefficients. Then how we will represent? We will represent like this. A, possibility of being in 0, 0 state, plus B, possibility of being in 0, 1 state, plus probability of C being in 1, 0 state, probability of D being in 1, 1 state. Okay. So this is the superposition state. We can represent it here. Okay. So this is the superposition of all these 4 states now. Because now the basic state are 4. This is, and this one. So the basic state is 4. So it will be a superposition state, will be the superposition of combination of all these basic states. That is 4. Okay. Previously, when there is a 1 qubit, there is a superposition of only 2 states. So for the 1 qubit, only 0 and 1 are the 2 states, cat 0 and cat 1. So superposition state is alpha cat 0 plus beta cat 1, right? And if we are assuming that there is an equal possibility of being in 0 and 1 state, suppose if we are assuming, then the coefficient alpha and beta, the normalizing condition is saying that alpha square plus beta square should be 1. This is the normalizing condition. And when we will follow this normalizing condition, alpha and beta are same. That is alpha square plus alpha square is equal to 1. That is alpha is equal to 1 by root is equal to beta. Like this. Okay. Alpha is equal to 1 by 2 is equal to beta. So if we are taking equal possibility of being in 0 and 1 state, then alpha and beta comes out to be 1 by root 2. That's why the same thing is in the Hadamard gate. When there is an equal superposition of 0 and 1 base, so the 1 by root 2 factor was there. So now here, come here. So we, if is the same thing, we can, same criteria, if we can choose it here, then there are 4 states. So there is, if there is an equal possibility of being in all the 4 states, then the value of A will be coming like that, 1 by 4, means 1 by 2. Okay. So like that. So this is the multi-qubit, how to represent the multi-qubit input matrix. We have to take it the tensor product, and we have to take the number of states like 2 to the power n. Okay. And then after the number of states, we can represent the superposition state in this way. Okay. So now directly I am telling you what will be the tensor product of the superposition states. Okay. And there is a very simple rule to follow that. Yes. Now we are having for the 2 qubits, we are having 4 things. Okay. So first is CAT 00. Second is CAT 01. Third is CAT 10. Fourth one is CAT 11. Okay. So the else CAT 0 was having matrix 10. CAT 1 was having matrix 01. So now here I am directly just you can take the tensor product. I am directly telling you the tensor product will come out like that. There will be, see, there are 2 possibilities. So there will be total there are 2 things. Because it's single qubit, 1 qubit gate, 2 possibilities, 0 and 1. So there is total number of states are 2. So 2. Now the total number of states are 4. So it will come out to be 4. So at this place, only one, last place is 0. Right? So it will come like that. 1, 0, 0, 0. It will come like also. Now 0, 1, 0, 0. This will come like 0, 1, sorry, 0, 0, 1, 0. This will come like, see, 1. 1 is at here. That means 0, 0, 0, 1. Because here there are 2 states. Here there will be 4 states. See, just blindly you can write the 4 states, and in the last you can write a 1. 0, 0, in the last you can write a 0. Okay. So right, this is like this. So these are the input matrices of these states. Okay. And I should say this one belongs to this one belongs to this belongs to this one. I hope everything is clearing here. Okay. So these are the input matrices, and we know this is the transformation matrix for multi-qubit gate control node or control Z, like that. Okay. Swap gate like that. Pauli gate like that. Only is remaining mathematically what we can do. We can multiply this thing with this, then this thing with this, these things with this, and this thing with this. For each thing, we will have an output. So we will have a 1, we will have a second output, we will have a third output, we will have a fourth output. So all the 4 outputs we will have in the multi-qubit gates. Okay. This is for the mathematical point of view. Now I'm coming to the understanding point of view, how we can understand the control NOT gate. Okay. Yes. So I have to take a 1 minute break. Okay. So I'm coming right back, right after 1 minute. Okay. Then we will tell you about the physical understanding of this. Yes. So I'm right back. Yes, we were talking about. Yes. So we were talking about the understanding of the C0 gate, right? So let's delete this thing. Yeah. Yeah. So C0 gate is a very simple operation. A very simple operation to say that first thing you can say that there is one example I want to quote you before starting this understanding of C0 gate that uh, everybody is running the TV, right? Or everybody is having the habitual to operate on the MCBs and fuses in their houses, right? So suppose the TV, if you are running a TV which is operated by the remote, okay, this TV is connected in this socket. This TV is connected in this socket and it is operated by the remote control like this, okay, remote control. So this is TV. Okay, so this TV is up. One, hello, we have 1 minute. I think I have muted myself. No, okay. Yeah, yes. So, uh, hmm. So your remote has a button of on and off, on and off. Your remote has a button of on and off, but you can operate the TV remotely by on and off by this button. But this button, when you are pressing this button, TV is going on the on mode. When you are again pressing this button, the TV is going on the off mode, right? But this button will work only and only when the TV is on from the switch or circuit. If it is on, if on, then remote work. Then remote will work. If it is off, it will not work. If off, it will not work. Remote will not work, right? The same fundamental is there. So, or in the houses, there is a MCB. When there is a MCB, the MCB is off. No operation is going on in the home. Okay. When the MCB is on, every operation we can perform and we can control in the home, but the MCB off, nobody can control the operations. Okay, so like that, based on these funda, we are giving an extra control on the this 1 and 0. Okay, so the extra control is called, that's why we are writing here boss mode good. Okay, means it's just like a boss. Okay, so the concept is also inspired from the classical control flip. There was a flip flops. There are a lot of varieties of the flip flops. We are taking feedbacks in the flip flops. We are cutting the feedbacks in the flip flop. There are latches. All the things are there in the Boolean algebra. Okay, flip flops and resistors and all that. But in the quantum computation, there is a one concept called entanglement, which we will discuss when we will deal with the algorithms. Okay. So, uh, to tackle the entanglement concept, so this David again, which is one of the founder of the algorithm also. So that has given this logic gate. He has shown that C naught plus single qubit gate, okay, which work as a universal gate, and that universal gate we demands. In the classical also, you will be remembering that there were there was NAND gate and NOR gates, which were the universal gates, right? So at here, so David has searched in the search of the universal gate, and they have searched like this, that C naught and one single qubit gate will work as a C naught means control, and one single qubit gate will work as a universal gate. So how to do this? Let's see one more operation with this fundamental things. Okay, so let's clear all these things. For that operation, we are making this these two wires, and among the one wire we can get one input one. This is the input one, because there is a multi-qubit gate, so input will be more than one. So this is for input one. This is for input two. So on one input, okay, we will leave it as it is, but on the second input, we will apply one operation gate. Okay. On the second input, we will apply one operation gate, that operation gate is X. Okay. So it is our choice, but we are understanding C naught gate, and X is working as a NOT gate. Why X is working as a NOT gate? So we are taking this NOT gate at here. Okay. And C for control, to control. So input 1 is used as a control. Input 1 will used as a control to control this gate, that is X gate. That is the operation which is going to perform at here. It is a NOT gate operation, right? NOT operation is going to perform it here. So the NOT operation is going to perform here, but with the control of this. If this control is 1, then this operation will perform. If the control is 1, then this operation will perform. If the control is in 0 state, means cat 0 state. If it is cat 1 state, this operation will perform. It is in 0 state, this operation will not perform. Right? Okay. So in the output, the input terminal 1, the control will remain as it is in the output. Remain as it is in the output. That is input 1. But sorry, this is called output 1. Okay. So we will write it like this. Back. Output 1, which will be equal to the input 1. Okay. But at here, for this output 2, we have two conditions. If the control is 1, then there will be a not of input 2. If control is 0, then will be a input 2 only. Sorry, then this output 2 is equal to the input 2, like that. Okay. So this condition will follow. Now we will take one example. Suppose we are applying in the multi-qubit gate. If we are taking 2-qubit gate, so in the 2-qubit gate we are having 4 states: 0 0, 0 1, 1 0, and 1 1. So suppose we want to apply 1 or 2 states, we can see the example. So there is an input 1, input 2. Here is a control X gate. So suppose we are applying this one. So this is work as a control. This is work as a target. Here this is a control, and this is we are taking as a target. Okay, because it is targeted by the control gate. It is targeted by control gate. That's why. Okay. So at here also, one we are taking as a control, other we are taking as target. So control is reaching in a 0 state. Target is also reaching in 0 state. So when the control is in 0 state, the rule is that whatever be the things in control, it will remain as it is. So output is always equal to the input 1. So output 1, this is 1, output 1, is always equal to the input 1, that is 1. Oh, sorry, 0. So this will come as it is, 0. Okay. Now at here, because the control is 0, so it will not work. So when the X gate will not work, the function of the X gate is invert, but it is not inverting. So 0, it is remain as it is at here. Okay. So this condition will apply. This will apply here. Okay. I can take a different. Yes, this condition will apply at here. Control is 0. So the output 2 is always equal to the input 2. Okay. Now, so the output is, output 1 and 2. Output is 0, 0. Output is 0, 0. Like this. Okay. So if we form a truth table, so the 0, 0 output is 0, 0. Now see the another control, this one. If we place this one, 0 and 1. So 0 and 1, 0, and now here 1. So 0 will remain as it is, 0. Okay. We will remove things right here. 0 will remain as it is. And because it is 0, it will also not work. It will not fill it. So 1 will come as it is. So it's 0, 1 will also come as a 0, 1. This is first is 0, second is 1. Output 1. This is output 1. This is output 2. Okay. Now come to the 1, 0. Now the things will change because in the control 1 is here. Yeah. See. So when in the control 1 is here, here is 0. Okay. This one, this condition we are talking about. So when control 1 is here, so whatever be the condition, control 0 or 1, irrespective of this condition, here the output will come as it is. 1 will come as it is. That is 1. But at here, now the X gate will come in active stage. Okay, active state, and X gate will perform its function. Its function is to invert this. So when it will invert this, invert this, you will get a 1. So the output is 1, 1 here. Okay. So when the control is 1, 0, so output here is 1, 1. Now if we will watch it, oh, right. Now see the fourth one, this one, 1, 1. So this is 1, this is 1. So this one, when control is 1, then it is same coming as it is 1. Sorry, coming as it is 1. Okay. But since it is 1 and it is in operating condition because control is 1 now. Because the control is 1 now. So it is an operating condition. Its work is to invert. Invert means 1, invert, we will get a 0. So output stage, we will get a 1, 0. So for the 1, 1, we will get a 1, 0. See here. 1, 0 is getting invert to the 1, 1 state. And 1, 1 state is getting invert to the 1, 0 states. These two are interchanging. This coming to this coming to this. Okay. So this is the output or truth table for the C NOT gate. This is called C NOT gate. Okay. Or we can call it CT gate also. T for target. C for control. Okay. So this is the multi-qubit gates. Now in the same pattern, there are 2 or 3 more multiple qubit gates are there. Okay. So from the Wikipedia page, you can follow the transformation matrix, and for the input matrix, you can have a outer product or you can have a tensor product. Okay, for the matrix. So that's it from my side. And any query or something, you can chat in the chat box. Otherwise, we will going to end this session. Is there any query? You can chat me. So anything you want? So, yes, certain, okay, not. So Anand raised hand. Is any query? Please put in the chat box. So if not, then we can end the session and we will start the quantum circuits in the next session and series and parallel quantum circuits and some Qiskit programming along with this. Okay. So, okay, now I'm ending the session, handing over to Susmita.
Hello, yeah, yes, sir. We can wind up. Thank you.
Okay, thanks.
Thank you. We'll meet again by tomorrow. Thank you so much. Yeah, so dear faculty members, the attendance link is on a chat. Kindly mark your attendance. And some are asking for the materials. Yes, the materials which we are going to upload in LMS. So I request please be waited till tomorrow. By tomorrow EOD, you get all the materials in LMS. Okay. I think we can good to go. We'll wind up further. Thank you all. Thank you for joining. We'll meet again by tomorrow at 3 p.m. Thank you, everyone.